This lesson will be about 2.2 and 2.3. So the things that you're going to need when you start viewing this lesson on linear models is going to be, of course, this worksheet called Video Notes. You're going to need a blank note card. You can use one with lines on it. You're going to need your graphing calculator, and you're going to need your textbook. I'm hoping that you've already read over 2.2 and 2.3. If you haven't done that yet, you might want to pause this video right now and look over that lesson. It's 2.2 and 2.3. There's going to be a lot of new vocabulary as we go through this, and this lesson will be really quite long for the video, but that's just because there's so much new stuff being thrown at you and a lot of new terminology. But we'll try to sort through it. We're actually going to work on this for 2 full days in class, and it's really better if we just dive in and learn it all at one time rather than learning it a little bit in 2.2 and then having to add on a little bit more in 2.3. So if you need to gather those things or you need to look over that lesson before we begin, go ahead and pause the video and do that now. The question that was asked is, what is a linear model? And of course, whenever we look at the word linear, we're looking at the root word line in here. And the root word line means that it's going to have something to do with lines. So a linear model is going to be a model of one variable as a linear function of the other variable. So we know linear functions to be lines like y equals mx plus b, and so we're using the variables x and y as our independent and dependent variables. So that's the same kind of thing that we'll be talking about here. We'll be coming up with some kind of a model or an equation, and it will be linear in nature, so the variables in it won't have any squares or cubes or half powers or anything like that, and it's going to be totally a linear equation. Alright? So the example that we're going to start with says this. It says, jewelers emphasize that the price of a diamond is determined by cut, carat weight, color, and clarity. The table at the right gives carat weights and approximate prices in US dollars for 20 diamond rings sold at a recent auction in Singapore. All the rings are of the same quality gold and contain a single diamond. Enter the data in the two lists, the weight in list 1 and the price in list 2. So I'm going to write that on top of here. You can write it down too. This is list 1 and this is list 2. So you're going to need to go into your editor, Stat Edit, and I'll show you I have mine already typed in, and you're going to want to put those in list 1 and list 2. So right now you're going to want to pause the video and you're going to want to enter those two things in list 1 and list 2 and then double check them. Several of the numbers in list 2 end in 50 cents. So you're going to want to be very careful when you type those in. So pause the video now and get that typed in. After you get that typed in, let's run the one variable stats for each list and let's see what the sum should be. The sum for this list should be 4.24. So if I go stat, calculate one variable stats for list 1, the sum is 4.24. And then if I go stat, calculate the one variable stats for list 2, I get a sum of 15873, so 15,873. So you want to double check and make sure you have those as your sums. If you do not, then you've made an error somewhere, and so you need to pause the video, you need to find your error, fix it, rerun the one variable stats until you get those two sums. Because we're going to do this together, and it's very important that we have the correct data in the calculator. Okay, next thing we want to do is make a scatter plot of the data. Now the scatter plot is going to be under the same place where we found all the other displays that we were graphing in the first chapter. So it'll be where we can find the box and whiskers and where we can find the histogram. So to find that, we're going to go to second y equals. Okay, now my calculator is still set up to do the modified box plot here, so I'm going to hit on to turn this on, and I'm going to come down to type, and the first thing in type is the scatter plot, so I'm going to choose that one. And then immediately it asked me about my X list and my Y list. And I do want list 1 to be my X list, and I do want list 2 to be my Y list. So, for example, these are your X's, and these are your Y's. So we want to keep that. You can scatter plot with either a little square, a plus, or a little dot. Doesn't really matter to me. If you have a preference for that mark, you can change it. So to fit this to the window, we're going to use the Zoom 9 feature. Remember, on histograms we couldn't use that, but on Box and Whiskers we could. And here's another example of where we can let the calculator choose the window for us. So we'll go ahead and go Zoom 9. Let me try that again. Zoom 9. And then here is my scatter plot. Okay? So the calculator set up a window for me that goes from 97,000 to 373,000, and then 114.435 up to 1,849.065. Okay, that's what it looks like. Yours may look a little bit different than that. Next step is to now find the line of best fit. The line of best fit. So the first thing you're going to notice about this data is that it looks like it could make a line. It looks like it's almost set up so that we could put a line on there to connect the points, and the line would go very close to or through several of the points. So to do this, we're going to let the calculator find what's called the line of best fit, not just any line of best fit. When you were in middle school or Algebra 1, you may have done a line of best fit on a scatter plot that was given to you on a piece of paper by just finding a couple of points on here and drawing your line with a ruler and then finding the slope and the y-intercept and so on for that. Well, we're not going to do that. We're going to use a method on our calculator where we find the line of best fit. There truly is one exact line of best fit, and we're going to let the calculator help us find what it is. And it wouldn't matter if we had a Texas Instruments calculator or a Hewlett-Packard or any brand of calculator for that matter. The algorithm for finding that is the same on all calculators, so it will be the line of best fit. So to do this, we're going to calculate a linear regression. A linear regression. And to do that, we're going to go into our Stat Calc menu on the graphing calculator. So I'm going to go to Stat. I'm going to go over to Calculate. And this is where we find 1 and 2 variable stats. We're going to go down here to number 4. And number 4 says LINREG. That stands for linear regression. And then AX plus B. So it's kind of like Y equals MX plus B, but they called it AX plus B. So we're going to choose that. And then after we choose that, my X list is really list 1, and my Y list is list 2. Now, if you have another calculator, it comes up, the older TI 83s and 84s, it comes up and it says linear regression, and then it's just AX plus B, and then it's just the cursor's just blinking right here, and then you're going to type in L1, comma L2. Okay, so you have to go second L1, and then you have to get the comma. The comma is right here above the 7, and then you'll need L2 on that. Okay, so you'll have to go second L1, comma, second L2, and then you'll hit enter after that. But don't forget to put the comma in between. Okay, once you hit enter, it brings this up on the screen, and it says Y equals AX plus B, where A is 5501.527207 and B is negative 372.673768. Okay? So your A value is approximately 5,501 point, I'll go ahead and write all the digits out this time, 527207, and the B is approximately negative 372.673768. Okay? So what is the approximate line of best fit? Well, that would be Y is approximately, and then notice we're going to plug in this A value for A and this B value for B. So 5,501 point, I'll say 527 X minus 372 point, I'll go 674. Okay? You can pretty much round to whatever you want on that, because you're going to put the approximation symbol, and whenever we write those down, we'll just be writing them down as a point of reference. We're not really going to use that equation for very much because we're going to want to put a more exact equation in the calculator and graph a more exact line. Okay, well, let's stop and talk for just a minute about what that slope of that line is telling me about the average rate of change in this problem. We all know that slope means the change in y over the change in x, doesn't it? The change in y over the change in x. Well, the column over here for our y's represents the price, and then the column for x's represents the weight. So this would be price, so that's our x, our y, okay, and that would be, let's put that as dollars, and weight, which is in carats, right? So it's talking about the price per carat. That's what it's talking about, the price per carat. So the slope, change in y over change in x, represents the price per carat weight. So the slope tells the average rate of change. Let's call that the average rate of change, all right, in the price per carat for a diamond ring. And that would be approximately $5,501.53, wouldn't it? Okay? Because our slope was this A value right here, it's telling us that the average rate of change from 1 carat to the next carat to the next 4 carat and so on would be approximately $5,501.53. Now the next thing it wants us to do is to graph this line along with our scatter plot on our graphing calculator. I'm going to show you how to do this, and then we'll make a note card with those commands on there for making that scatter plot so you can find that equation of regression line anytime you want to by yourself. Okay? So to do that, we want to put this in the y equals because that's how we plot lines. So I'm going to go to my y equals. I notice that my stat plot is turned on, and that's fine because I want to get those points still graphed. I'm going to go ahead, once I'm in my y equals, and I'm going to go over here to this vars button right here. Remember vars? Okay, we're going to go to the variables button. We're going to go down to number 5, statistics, and then here's where we could pull up. You might remember we had standard deviation was our SX here, and population standard deviation. Well, I want to go across with my right arrow here so I get to EQ. And when I get to EQ, you just see the choice number 1 says REG EQ. Well, that's the regression equation. The last regression equation calculated is this one right here. This is the one that's in my calculator. So I'm going to select that, and then it enters that into that Y1 area there, so that I don't have to type this in by myself. Now you're going to notice that there are a lot more decimal places than there were on these when we saw them on our screen. You can see that we have up to this 7, and there's 1, 2, 3, 4 more, and so on. So this will be an even more accurate line because it's using even more decimal places. And once we have that in the y equals, all we have to do is hit graph, and it'll add that line right onto our scatter plot. Pretty cool, isn't it? All right, so let's stop here just a minute. Let's get your note card and let's just tell what we did. So I'm going to bring up just a piece of plain white paper here, and we can write on this. We can call this note card. Oops, hang on. Okay, I'm going to call this note card 2, 2, and 2, 3, and it's going to be linear regression, also known as the line of best fit. Okay, and then what we want to put on here was how we would get the data in our calculator and then do a line of best fit. Okay, so you're going to say enter data into, I'll just say L1 and L2. You can put X's under here and Y's under here if you want to. Okay, then we went to stat, calculate, and then we chose number 4 because it said linear regression AX plus B. That was the one we chose. And then the cursor was blinking, so we picked L1, and then I'll make a thing that says comma on it here, comma, L2, and then we had to hit enter. Okay, that comma is above the 7, remember that. Okay. Then, to make the scatter plot, we went to the second, y equals, okay, and then we had to hit enter, and then we had to turn our stat plots on, and then for type, remember we picked this one that looked like a scatter plot, okay, that's the first choice, and you just need to make sure that the X list is list 1, and then the Y list is list 2, right? And then all we had to do was hit zoom 9. Zoom 9. Okay? This will graph the scatter plot. Now to get the line of best fit on there, we're going to go to the Y equals button. Alright? Clean out anything that's in there, if you have anything in there. And then we're going to go to that VARS button. And then we pick number 5, statistics. And then after that, I think we had to use the right arrow twice. And then we chose EQ, didn't we? Okay, then after we chose that EQ, we picked number 1, which said regression equation. And then I think we hit enter, and then we hit the graph button. And the graph button would then graph the line with the scatter plot on our window. Alright? I think that's what we did. We'll try that out. We'll try this out on many different things. We will not do just linear regressions. These will be the commands for everything that we do. Even when we do exponential or quadratic or some other kind, we'll just change to a different kind. We won't pick number 4 here, but all the rest of this stuff will stay the same. Alright? So that's going to be our note card. If you need to pause this and look at this for a while to get caught up with me on writing the note card, that's fine. But that's what we need to have on our note card for our commands. Okay, now what we're going to do is number 5. It says we can use this line of best fit to make predictions based on the line of best fit. You're going to use your model to predict the price of a 3/10 carat diamond. Okay, when you hit your trace button, what you're going to notice when you first hit the trace button is where it says P1 colon L1 comma L2. If you start moving around with your right arrow, it's going to jump you around to the actual stat plot point. So these would be the points in the table that we graphed or we entered in our list, our 2 lists, because I'm on my stat plot. If I want to do something with the line of best fit, I have to hit my down arrow until this says y equals up here, and I now have my equation of my line in there. And then I can trace on that line. So I want to do a 3 carat, a 3/10 of a carat. Well, that's an X value. So if it's an X value, I can hit my trace button, and I can tell it I want, oops, I hit my down arrow, I can tell it I want 0.3 or 3/10, and I can hit enter. And when I do that, I get that y is equal to 1277.7844. Well, I'm going to answer this question over here. It's in dollars and cents, so I'm going to say it's approximately $1,277.78. That's what my 3/10 of a carat diamond would cost. Okay, new vocabulary word for you. This prediction is known as interpolation. Okay, interpolation, or it's called interpolation because the 3/10 carat, that carat weight, lies between known values. In other words, if I go back up here and look at my data, my smallest carat weight and my largest carat weight are smaller than 3/10 and larger than 3/10. You see I have one bigger than 3/10 right here. I have some smaller than 3/10, you know, like here. So I know that 3/10 lies in between the values on this chart. Okay? If it does lie within the values on the chart, then we call that interpolation. Interpolation. So that makes that a fairly accurate prediction based on this set of data because it's an interpolation. Okay? Well, if we go to the next page, it says, use your model to predict the price of a 500 carat weight. All right, so I'm going to type that in, 0.05. And right when I hit enter, I'm going to get what's called an invalid error. All right, and you can go to where the error is, and let's see where it is. And it says, well, 5/100 is invalid. So are they saying you can't have 5/100 of a carat? Because we know we can. That just gives a little tiny diamond chip, so we know we can. The error is in the window range. If I go to my window, remember my window goes from, it fit it to the window, so it's going from 0.097 up to 0.373. So it's using those values on my table. And so this 5/100 is less than that. So if I just choose to put a 0 in here, I'm just going to change this to a 0. You can do that too. And just go ahead and hit enter, and then go back and hit graph again. It'll put your scatter plot points on there and your line on there again. And then you can hit trace. You see you're on your stat plots, so hit your down arrow to get onto your line again. And then you can put 5/100 of a carat in here, and you can see what it would give you. Okay, well, according to this line of best fit, it would give me approximately negative $97.60, right? Negative $97.60. Okay, so let's talk about this for a minute. We got an error, and the error said we had something, whoops, invalid, okay, and that was the window range. So it was a window range error. And now we wind up with a prediction that we have a negative amount. So in other words, if you had a 500 carat diamond ring and you took it to this auction in Singapore, they would give you $97.60 to tell you to keep your ring. Okay? Probably not going to happen. Okay? This is called extrapolation. Okay? Extrapolation is happening here because this 0.05 carat weight lies beyond known values. If I go back up to my chart, I don't have anything that small in my chart, do I? Let's see, what's our smallest one? Is it 1/1200 of a carat? It must be about 1/1200 of a carat. So in other words, they were trying to do a prediction for something that doesn't belong within our set of known values, the range of our known values. Okay? It wants to know which one of these estimates then would be more correct. The one from number 5, where we were doing a 3/10 carat diamond, or the one from number 6, where we're using the 500 carat diamond. Well, and remember, they're asking you about the estimate. They're not asking you if 3/10 is more accurate than 5/100. You can weigh the diamond in the ring. We know that that would be accurate. They're asking you about the estimate form. So they're asking you, is the estimate of $1,277.78 or the estimate of negative $97.60 more accurate? Well, the estimate of about $1,277.78 is more accurate than the estimate of approximately negative $97.60 because the estimate for the 3/10 carat ring is interpolation and the other estimate is extrapolation. Your line of best fit is really only accurate for the data that you include when you put it in the two lists. And all the values that lie in between there, it can be fairly accurate for those. It's inaccurate if you're making predictions that are a lot smaller or a lot higher in the X value away from that particular data set. And this is really ringing true on this problem because they're not going to pay you to leave and keep your ring, are they? Okay? So remember, this is asking about the estimate, not about the weight of the diamonds, but the values of them once we put it into our predictions on our line of best fit. To measure how well a line models data, we calculate the residuals. Residual is another name for error. And you might have heard that residual in a different way, like residual effects of something. For instance, my husband had cancer and he took a lot of chemotherapy, and one of the drugs that he had in his chemotherapy was a drug called oxaliplatin, and one of the residual effects of that is nerve damage to his extremities. So he doesn't have a lot of feeling in his hands and feet. Those are his extremities, and this can cause problems. It can happen, a lot to elderly people or diabetics and so on. They can have residual effects and things. So it's something that is like lasting in your system, that kind of thing. Okay. Well, in this case, we're talking about residual being the amount of error. All right. So an observed value is going to be a value that comes from the data table. So if we're thinking about our diamond rings up here, we should be thinking about all of these amounts were actual amounts that they purchased. These carat weights were the amounts that they purchased. Okay? That's an observed value. That's when you go out and collect the data. A predicted value is a value that comes from the model. In this case, our model is the line of best fit. Later in the chapter, we'll do other models. We might have a quadratic model, an exponential model, a power regression, those kind of things. But for now, it's the line of best fit. And the error or the residual amount is the observed value minus the predicted value. The observed minus the predicted. So they would like us to calculate the residual for the 0.2 carat diamond. The 0.2 carat diamond. So what we're going to do for that is we're going to go to our chart and we're going to find a 0.2 carat diamond. It's about, I'd say, a third of the way down from the top there. Okay, a 0.2 carat diamond. Did you find it on the chart? Okay, its observed value from the chart is $747. Now we're going to go to our prediction here, and we're going to type in 0.2, and we're going to say the predicted value for this would be 727.63167, right? So that's when x is equal to 0.2 and y is equal to this amount right here on the line, right? Okay, so when we subtract those, we get about 19.36833. So this would be about $19.37 difference. $19.37 difference. Alright? Now we're going to do the same thing for a 0.33, a 3300 carat diamond. So again, go to your chart and locate the 3300 carat diamond. If you need to pause this and grab your paper and do that, you can. The observed value should be $1,417.50. Okay, now we're going to go over here to our line of best fit and type in 3,300. Hit enter, and we come up with $1,442.8302, right? So this is off by about negative $25.33, isn't it? Okay? So one error is above and one error is below. So here's a little note you can make to yourself. Error can be positive or negative. Now if we go back and observe where these are, I don't know if you can see it very well on the line of best fit, but when we do our 0.33, okay, that point is right there. It's on the line, but maybe just a little bit under the line. To go over here to the 0.2, where that cursor is blinking, do you see that that is just a little bit on the left side of the line, just a little bit above the line. So that's why we're having a positive and a negative on that. Okay, and you could make many, many other predictions and find the residual or the amount of error between what the chart is telling you and what the line of best fit is telling you. Okay, the next thing we want to talk about then is the definition of the sum of the squared residuals. The sum of the squared residuals. See the sigma notation where it says I equals 1 to n, and we take the observed y sub 1 minus the predicted, or y sub I minus the predicted y sub I. So in other words, we would be taking those prediction values that we get over here in our y's, like we just did above, to see how much money the model is telling us we should pay. So we would subtract the observed minus predicted, and that would then give you the error, right? And then you would square that. And again, we have to square the error because sometimes the error is negative, sometimes the error is positive. So it could all just cancel out, and it'd be like we don't have any error, but we really do have error. So the sum of the observed minus the predicted y values squared is the sum of the squared errors. Okay? So the sum of the squared residuals, or the sum of the squared error, is a statistic that measures the lack of fit. Not how well it fits, but how well it doesn't fit. Okay, when you find the line of best fit, which is what you find when you do by hand, when you do the calculator, it's also known as the least squares line, or the regression line. It was discovered by the French mathematician Adrien Legendre in 1805, and his approach to the problem is called the method of least squares. The method of least squares, because he used the sum of the squared residuals to determine the linear equation for best fit. So what he actually did was he took this scatter plot, whatever it was, and he tried a whole bunch of different lines on there. And he tried to figure out how far off the line each point was and made a little square there. And then he added up the area of all those little squares to see what he could get to get that to be the least. And then he would tweak the line by moving it a little bit more this way or a little bit more back this way, trying to get those squares to have the least amount of area. I'm going to show you a little application of that when we get to class the next time on a little thing that I found, a little computer applet that I found, so I'll show you that when you get to class. But what it's going to do is show you that the line of best fit has these two properties. It minimizes the sum of the squared residuals, so it wants the least, minimized means the least, right, amount of squared error. So that's just code talk to say it's going to minimize the error, it's going to have the least amount of error, and there still may be a lot of error, but it's going to give you the one with the least amount of error. And then it contains this point called the center of mass. Okay, the center of mass. And that's also called the center of gravity. And it is the ordered pair x bar, y bar. So it's the mean of the x's and the mean of the y's. So one of the things that Ginger figured out was that to have a place to start when you have this whole scatter plot full of points and you're trying to line up something, is to get the mean of the x's and the mean of the y's and plot that point. So he would plot that point. And then he would take his line and run it through there, and he would tweak it, pivoting around from that point. This is the only point right here that's guaranteed to be on the line of best fit. There don't have to be any other points on the line of best fit. They all may lie above it or below it, which is different than how you were first taught to do that in algebra when you took a ruler and you just joined 2 points together. But none of the points actually have to lie on the line of best fit. Let's see if we can find the center of gravity or the center of mass for our data right here. Okay? So we can go to Stat Calculate, and you could actually go down here to where it says 2 variable stats. 2 variable stats. You could hit Enter. Now my calculator comes up and says L1 and L2, but if you did 2 variable stats, you may have to type in L1, comma L2. Anyway, we're going to come down here and we're going to calculate this. And it's going to tell me my x bar. Okay, I'm going to try to get x bar, comma y bar. Okay, the mean of the x's is 0.212. If I just scroll down here a little way, the mean of my y's is 793.65. And those, I can tell, are not rounded. So those are going to be exact. Okay? Now remember I told you you wouldn't use your line of best fit for very much? We wrote that down at the very beginning. We had y was approximately equal to 5501.527x minus 372.674. Do you remember that? And I said you really wouldn't use that line for anything. Well, the only thing that you're ever going to use it for is this right here where you verify by hand. You want to show that this point is on this line. Now, you might say, well, wait a minute. I could just go here and type in 0.212, and sure enough, it gives me 793.65. But that isn't verifying it by hand. Okay, so we're going to put this amount in for our y. We're going to say 793.65 is approximately equal to 5501.527 times our x amount, which is 0.212 minus 372.674. So I'm going to say these are approximately equal. So 793.65 is going to be approximately equal to this amount over here. And let's see if that's true. Okay? So we're going to take 5501.527 multiplied by 0.212 and then subtract 372.674. And we do get that because we get 793.649724. So you're just verifying by hand that that truly is the center of gravity or the center of mass. It says also verify this by tracing it on our model, and I showed you how to do that. We go to our graph, we go to trace, we use the down arrow to get on the line, type in 0.212, and sure enough that line, or that point is on the line of best fit. Okay. The next thing we're going to talk about is something called correlation. Correlation coefficient. Correlation coefficient is used to measure the strength of a linear relation between the two variables. It's denoted by the variable r. I don't know why they chose lowercase r, but we always label it with the lowercase r. Okay? The correlation coefficient describes the direction and the strength of the relation. Extreme values of 1 and -1 indicate perfect correlation. So if this is a number line, and this is 0 in the middle here, and this is 1, and this is -1, 1 would be perfect, positive correlation. -1 would be perfect, negative correlation. If the slope of the line of best fit is positive, it will have positive correlation. If the slope of the line is negative, we'll have negative correlation. So it's not better to be perfect positive than it is to be perfect negative. What we'd like to have is something really, really, really close to 1. Okay? And the way linear correlation works is, if you get in here, you get weak. So you could have weak positive or weak negative correlation. You can then have moderate positive, you have moderate negative, and then we can get up in here where we have strong positive. We can be in right in here where we have strong negative. But it's not all divided up just in thirds. Right? If you have strong, you need to be 0.8, 0.9, somewhere in there. Your moderate is somewhere around 0.75, 0.6, somewhere in there. You're getting pretty weak at 0.5. So you're pretty weak about right in here. If you get something down in here, 1 tenth, 2 tenths, 3 tenths, and so on, that's going to give you pretty weak correlation. Okay? And correlation is only going to, this kind of correlation is only going to work for linear relationships. Okay? Linear relationships. Now, your calculator, there's a very, very complicated formula for finding the value of R. But your calculator can find that for you. You just have to tell the calculator to do it for you. And it'll do that right away when you calculate the line of best fit. But it only works if you have a feature turned on your calculator. Now, I don't know if any of you noticed that when you go to Stat Calculate, number 4. Some of you may have already had, when I calculated this, may have already had something called R and R squared listed down here. But if you don't have that, it's just because that feature is not turned on your calculator. So I want to show you how to do that. So let's clear our screen, and I'm going to show you how to turn that feature on so it'll be on for all the linear regressions you do from now on. Okay? Well, what we're going to do is we're going to go to our catalog, and the catalog is second 0. We'll go to second 0, and we'll bring up the catalog. This is the catalog of every function in your calculator. So if you only remember that you can do something, like you remember, oh, I've done this on my calculator before, but I don't remember what menu it's under, you could always go to the calculator and, the catalog, and you could search for it. Notice how the feature for alphabet is already turned on, and I want to go to the D's, and so the D is right above the X to the negative first power of the matrix button right here. So I want to get down to the D's, and with my D's, I want to scroll down now until I come to something that says Diagnostic On. Do you see Diagnostic On, and the little arrow is pointed to Diagnostic On? Yours is probably turned off right now. We want to go to Diagnostic On, and we want to hit Enter. Okay, and then the cursor is blinking, so we're going to hit Enter again. And then it should tell you that you're done. So once again, what we did is we went to Second Catalog, then I went to the D, which is right above the matrix, or right on the matrix button there. And then I scrolled down until I found Diagnostic On, and then I hit Enter twice. Okay, now when I go to Stat Calculate, and I do number 4, it's going to give me my linear regression, but it's going to give me the value of R squared and the value of R. Alright? We're not too interested in what R squared does, but we're very interested in what the value of R is. For this particular problem, our R value is approximately 0.9912. So it'll be right up in here, 0.9912. Not perfect positive correlation, but it is very strong positive correlation. Alright? Now, it should be positive correlation because as the carat weight increased, the cost or the price of the diamond increased, or the value of the diamond increased. So that was giving us, if we're looking here, we have positive slope to our scatter plot. All right? Well, we want to know what that correlation coefficient was. We found it at 0.9912. By the way, you can make yourself a note that Mr. Carl will always want 4 decimal places on that. I've only seen one problem in all the problems I've ever done where the correlation coefficient came out exact. Every other time it's been something that's been some irrational number that you've had to round. Okay? All right. So to describe then the direction and the strength of the relationship between the carat weight and the price. To do that, we would say there is a strong positive correlation between the size of the ring, well, I should say the carat weight, and the value. Okay? We could say, whoa, the correlation coefficient indicates that the model is a good fit for the data. It's a good fit for the data because there's such strong positive correlation. We'll talk some more about correlation and causation when we get to class. Now, what I want you to do is to finish these questions 14 through 17 and have those ready to go when you get to class. You're going to use your model, so you're going to want to go back to your graph. You can use your model. You're going to make some predictions. You can look back and talk about interpolation and extrapolation. It's going to ask you about some costs of things, and then it's going to ask you about some prices of things. And remember, the price is a y value. So if you want to do any graphing, additional graphing with the y value, you can go to the y equals and you can slip that in. Good luck.